Student and audience, and this is the next lecture. In the previous lecture, we investigated the dynamics of load-coupled converter, and we introduced some interesting dynamics of load subsystem, stabilizing load subsystem. So now we turn our attention on this source-coupled converter. So the title of this lecture is Alternative EET for the source-coupled converter. So EET has many variations, and this I know 3 important variations. First one is previous one, adapted to the load-coupled converter, and the second one is this one, alternative EET, which can be adapted source-coupled converter. Okay? So previously, if this is the directly connected, we are powering this downstream converter using ideal voltage source, which has 0 source impedance. Now we replaced this one. That means we are using practical DC source with finite output impedance. So this is a practical case. So this can be anything. This can be the fuel cell or lithium-ion battery, okay, or some degenerative due energy source, something like that, okay, new, strange, okay. So this is the practical one. This is the structure of this one, okay. This is the EET structure. I just take out this GS. So there is a GS because we are using practical source subsystem. It has some source impedance and is unknown because this source system structure of that is still unknown. Okay. So the filter and upstream converter, for example, any converter in the DC power distribution system, it's seeing the load converter, load impedance, and it is also seeing to the source impedance, source subsystem. So this can be any converter. Okay. So translate this like this. Okay. If you are interested in input to output transfer function with this GS present, we know the result without this, and GS is coming in, and its characteristic is provided or you measured, you simulate, so you have knowledge about that, and with that you want to know the transfer function from here to there. So this is the input to output, and this GS is extra element theorem. Locate A prime terminal, and H, the transfer gain, our interest is input to output small signal voltage transfer function, which is sometimes called audio susceptibility or input to output transfer function. Okay? All right. So this topic will be thoroughly covered. Topic 16. Some student said he hates this topic. Maybe there is no topic 16. Okay? So I don't know. So this is alternative extra element theorem. Everything remains the same. Everything remains the same. And this is the same. And the transfer gain of our interest can be any pair of circuit variable. Okay. Maybe this is the input voltage, output voltage as the previous example. Okay. G is the impedance of circuit element, will be located between this terminal, but its structure and the AC characteristic impedance characteristics are unknown, unavailable. Maybe it's the structure is not defined yet. It's not built yet, and they are building it. Maybe it takes the forever, okay, but eventually that will be there. And then we designate that as an extra element, okay. Situation is very similar to the previous case. And the previous case, we assumed this port is open, in this case, we assume this port is shorted. Okay? So previous case, G was infinity. Now this case, G is 0. Okay? So previous case was best suited for the load subsystem, right? Assuming the current sink and load impedance will come later. And initially we assume ideal voltage source, then this will be shorted. Later, G is coming in. So for that case, this is the method we're going to use. Okay, so this is the EET, but this is the alternative. Okay, this is the figure is the same, but initially we assume this is shorted. Okay, so H0 represent the input-output transfer function with this G is 0, this port is shorted. Okay, and this is the impedance of this component, and this is the null driving point impedance. This is the driving point impedance. Exactly same. Definition is the same. Everything is the same. But this H0 is the transfer function gain of this one with G is shorted. G is 0. Okay? So this is the slightly modification of previous EET. But this is the best suited for the case of source subsystem interaction analysis. Previous one was load subsystem interaction analysis. Okay, right. So why this form? Okay, we'll prove this, right? But if G is 0, then H becomes H0. That means this one is H evaluate under the circumstance G is 0. That makes sense, right? So equation previously this numerator and the denominator was swapped. Then we use infinity sign here. Then G is infinity. They become same. But now this becomes 0. They become same. Okay. So this everything is the same except this and this swap of this numerator and the denominator here and here, and everything the same. And this graphical illumination is the same. Okay, so we have 4 transfer functions. This one. Okay, we have equation. When G is 0, this becomes this one. So this is makes sense. It makes sense. Okay, so this is true, and this is the transfer gain. Evaluate with this for the shorted. Okay, then we have this equation. This one is defined same as the previous case. Driving point impedance and the null driving point impedance. Again, try to avoid any calculation. Instant network looking. And many cases, this null driving point impedance will be 0, or this one will be 0, or either one will be 0. Okay, but one, only one. Okay, two of them 0 when this becomes 0. Okay, or okay. Proof of this equation is very simple, extremely simple. Okay. So this is the original one. Okay. So this is original one, and this is the open circuit case. Here we assume this is the infinity. So this is the open. Okay. At that time, this is the equation. We proved this. This is true. Okay. This is the first EET, original EET, and you modify this. Okay. You multiply this by G in the denominator and the denominator, and you will have this. Okay. And in the numerator, you take out this. You take out this, then you will have this. Okay. And in the denominator, you take out G bar, then you will have this. This same equation, okay, nothing has been changed. Then maybe now you assume this is G is 0, then G is 0, this is 0, this is 0. then HS evaluate with G is 0. This is notation G0, H0 is this one. This one is H0. This one is H0. So H0 can be expressed as this one is replaced with H0. Then you have this equation. Okay. So we start from this structure, this architecture. Somehow we derive this. We just take out terms and we interpret this. This is H0 is this one evaluate at Hg equals 0, which is this one. Then replace this with this term with H0. Then this is alternative ET, and you can apply this situation. Okay. So just be formulating this formula, 2 steps. Then you have this situation. Then this is the equation for when we assume this is shaded, then we use this form, then that is this equation. Okay? When you assume this is open, you should use this. When you assume this is shaded, you just use this. Right? Okay? Okay. So application. One simple, obvious application is source coupled converter. So this is uncoupled converter. This is current sink, and this input is ideal voltage source with 0 source impedance. This uncoupled converter. And with this, we define this GIU, GOU, GUU. Okay, GS is 0. TMU, we can define everything same as the load coupled converter, uncoupled converter as the previous case. Okay. Now source is coupled and this is replaced with this. Maybe I should use this one prime because this is the Thevenin form. This is a Thevenin form, and if there is some element, this form is different. This should be the open circuit voltage appearing at the output. Okay. So assuming that, let me use this one consistently. Okay, that will simplify this description. Otherwise, I should use VS prime, something like that. Okay, so consider this, accept this. Maybe the only this series impedance is here, which is very rare in practice. Okay, but that is the case. Then we have this. So GS is coming in. Then this is the GIU. This is still uncoupled case. This remains the same because GS is this side. Okay, and this GOS. S means source subsystem, and TMS, AUS, source subsystem. Okay, and the input impedance seen by at this point is sum of this, sum of this one plus this one. Okay, because GS is this one, so still you use the notation of the GIU because GS is out of this interface. Okay, all right. Okay, this is the hard part. Okay. Okay, this is hard to explain, hard to memorize. Okay, hard to understand. But once you understand this just one time, then you can accept it. Okay, then everything will be very smooth, right? So this one. This is the small signal diagram to evaluate the audio susceptibility with this one, with GS here is GS. Okay, so it was GS, but it replaced with this current source, and we'll evaluate the impedance seen by this driving point impedance or null driving point impedance. Okay, this is basically this is the input impedance defined at this point is input impedance, right? Previously, when we are discussing load coupled converter, we used the output impedance of uncoupled converter because the extra element was at the output port. So this driving point impedance and the null driving point impedance, they are basically output impedance. Okay. Here, this EET was here. So whatever we see here, that becomes the input impedance. Okay. Variation of input impedance, that will help you to understand this. Okay. Okay. And this, again, this is necessary for the loop gain analysis. And from this structure, this Uy and Vo is the same voltage. If one is 0, the other one is 0, and something like that. Okay. And audio susceptibility with this, with GS is here, then this one, GS is not 0, but IO is 0, and this one is 0. Think about superposition. We are only considering one source, one disturbance source. Then audio susceptibility with source subsystem is audio susceptibility of uncoupled converter plus this one. This one is EET equation. I need some space in between. They are too crowded, but they are different things. So there's just some borderline here. Okay. Then this zeta bar is this, the ratio between this. Okay. We are considering the null driving point impedance. When evaluating null driving point impedance, output of transfer function is assumed 0. So this voltage is 0, but input is not 0. Input is not 0. Vs it's not 0. You are trying to find the transfer function of this. So this is not 0, but this one is 0. How that can possible? It's open. IC is 0. Okay. The only possibility of this case, VO is 0. With Vs is not 0 because this is output of this transfer function. Then means this IT is 0. Okay? When IT is 0, this is open. Then whatever occurs here, this will be 0. Input is 0. Output is 0. Okay? So for the case, you are evaluating ratio VT divided by IT. With IT is 0, then this becomes what? Infinity. Okay? Then this term is gone. All right? Because this becomes infinity, then you have this and this one, and the G bar is when you are evaluating this regular driving point impedance, then the input is 0, Vs is 0, Vs is 0, that is what? Regular. Just regular input impedance of closed loop regular input impedance of uncoupled converter, GIU. Okay? So this is the first equation. Okay? So input output transfer function with GS is simply this one. Okay? GS divided by GIU. GIU is closed loop impedance of uncoupled converter. Okay? Then think about this output impedance. This is the input, this is output, and the GS is not 0, Vs is 0, this one is 0. Okay. Then you have this equation, GOU, uncoupled output impedance, uncoupled converter output impedance, and we have this factor. Then we evaluate this zeta bar. When evaluating zeta bar, V0 is 0. Okay? V0 is 0. This one is 0. This one is 0. So this one is 0. Means IO is not 0. IO is not 0. Then means what? Output is shorted. Output is shorted. And if this one is 0, Vy is 0. Okay? Then this Vx is 0. So this one. No, not this. this one. I'm sorry, this one. We are talking about this one, right? So VO is 0. Output is shorted. So this is 0. Output is shorted. This is 0. Then this is 0. Means feedback is broken. So this is the open loop. Feedback is the open loop because UY is 0. So I use notation GI prime open loop output shorted input impedance. Extremely easy to evaluate. Okay, there is no feedback. Output is shorted. Then you can easily find from the small signal model. You can find the input impedance. Okay, this one is not easy to evaluate. Okay, but this one is extremely easy, very trivial to evaluate. Okay, and this one IO is 0. IO is 0, so it is open, so it really doesn't matter. It does not make sense. No, it's okay. It does not affect, and IO was initially 0. Maybe this is the redundant. Then with this open circuit, you take a look at this. This is what? GIUU. Okay, this is the input impedance of uncoupled converter. So we evaluate this. And this is about the loop gain. Okay, loop gain is a little bit tricky. So loop gain, input is this, output is this, and the GS is present. So we are using IT and VT. This is 0, this is 0. Okay, and this is the equation ET, alternative ET equation. This one we evaluate this, and Y is 0, output is 0. So UY is 0, UY, this is 0, and this is 0, okay? This is 0 with IO is 0, okay? This is open, and this is 0, okay? That does not mean output is shorted. This is the output is nullified, okay? So this is the output nullified, right? So this is 0, so this is the closed loop. Output nullified input impedance, GI double prime. This one is not trivial to evaluate. Okay, this one is not trivial to evaluate. Okay, try to understand this. This is the some you need something. Okay, but believe this. This is the output nullified. Output is nullified here. Okay, so this is 0. This is 0. When this is 0. Okay. Output is nullified. This one, the impedance seen by here with this UX is 0. UX is 0. This is 0. Feedback is broken. Open circuit. Input impedance. Okay. So this is I defined the GI triple dash double triple prime. Double prime, single prime, no prime, okay? GIU. There are 4 different input impedance associated with this. So very complicated. The reason for this is because in the previous load coupled converter, output was output voltage and the GL was located at the output. So they share one node. So many cases zeta bar becomes 0. Now it's different, okay? Because the position of this one is here with different condition. This determines the condition of evaluating this. So there are many different, 4 different GI are involved in this equation. Okay, so I summarize that GIs here. So in this analysis, we have 4 different GIU, closed loop input impedance of uncoupled converter. So this is difficult. This is the rather difficult. Looks simple, but it's not easy. Okay, it's not easy. Okay, maybe this coming Thursday, maybe there is a chance to evaluate this. We use EET to evaluate this actually. Okay, that is strange, right? EET. you have some difficult problem, think about EET, right? And this is GI prime is open loop is open, output is shorted. So this is the open loop, output shorted input impedance, very trivial to evaluate. And the GI triple prime is open loop, output is not shorted, open loop, input impedance, trivial to evaluate. And this is the output nullified, closed loop input impedance, not trivial, not difficult, not very difficult, not trivial. Okay, it takes some effort to evaluate this, and this one is most difficult among four. Okay, you may think this one is the easiest. It's not the case. The opposite is the case. Okay, this one is very easy. This one is very easy. No, easy, very easy, trivial. Okay. All right. Maybe I have some slide, but I cannot finish this up today. I have 10 minutes extra. Right? Okay. But I need to return everything, right? Yeah, summary, okay? Summary is good news, okay? All right, maybe you understand the procedure just one time and forget about everything, and just you don't have to remember this, just bring this table, this summary sheet, then you can use this, all right? So summary of transfer gains of source coupled converter. So this is uncoupled converter. Assume you evaluate this. This is possible because this is your design, your converter. So you have the entire knowledge about this. So this is okay, all right? And some guy else connected this. Okay, very complicated things. Okay, and when you are designing this, evaluating this, you don't have any knowledge about this, and you perform the design without this using uncoupled converter. And later on that is coming in, then you want to know is effect of that. You don't want to repeat every analysis again. That is very stupid and almost impossible, right? So you have your result and just add terms involved with this. There are only two terms, okay? So you take care of only two terms. Using the asymptotic approach, you are not touching equation. You are obtaining the graphical data and use the asymptotic approach to obtain your result. Okay. All right. So this is the audio susceptibility or input to output transfer function of uncoupled converter. This is the source coupled converter, and you only have one term here. This is the source, this impedance. And this one, they show you have knowledge of this, and this is one thing. And this is the graphical representation of GIU. And here, output impedance of your converter looks complicated. Let me move this guy. This, okay? So you have two terms here, and this is extremely easy to evaluate, and you have knowledge about this. And when GI is available, maybe one guy can be ignored and one term dominate. Okay, you ignore this, then addition of something in Bode plot. That is the one thing. And this one looks like this. Okay, it's a little bit intimidating. But this one is closed loop, output nullified input impedance. And this is open loop input impedance of this one. Okay? So knowing this is not difficult, right? Previous step was not easy. This, okay, this. But if you follow the step by step and think about the what try to remember what we are doing. Each one becomes 0 and so on. Then this is okay. All right. I first formulate this when writing the book. I spent some time on this. Okay. And I was not sure I'm entirely correct. But later on, using the simulation result, everything is okay. 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 Maybe we stop here. Okay. Don't give up this topic. Okay. So hard part is passing, and the application is very interesting. All right. Let me just say one thing. Suppose it's not a system, just one single converter, one single converter. All the converters should have this filter stage. Okay. Then the problem is exactly same. All right. So this is simple. Everything is known. But analysis of this, you need that formula, EET formula. Okay. EET formula. Otherwise, you will mix up. Okay? So people investigate this a lot because this is a very practical problem. If they have this to this converter, they should attach the in filter for the current filtering purpose. And in some case, there is overlap here, then converter becomes unstable. They didn't know that reason for 20, 30 years, okay? And finally, the EET will solve everything, right? So because of this problem was very famous, very well known. People call it in-filter interaction problem. In-filter induced instability, okay? A simple problem, but behind of that, there is a EET. EET provide all the equations to understand the phenomena associated with that. Okay? All right. We stop here. And this Thursday, we continue on these discussions. Okay? All right. Thank you. Hey, hello, everybody. This is the last part of lecture 2. This is lecture 2. Okay, so I went back the several pages because I made one minor mistake. Okay, so this is the previous lecture slide. Well, let me summarize this briefly. So this is our situation. This is the two-port network, and for our case, this is the converter, uncoupled. No, this is the coupled converter. But this impedance, one of impedance element, is unknown, undefined. Okay, so we don't have any knowledge about this. So there is a problem. So this is the initial problem. So there is a two way of solving this. One is assume this is not present. This is the open circuit. Then this is the first form of EET. And second approach is assume this is shorted. So here G is infinity. And now G is 0, then you will have this. Okay? So this is the EET, and this is the alternative form of EET. Okay? And we proved this relationship using two-port network and the condition of output null condition. Okay? So this is okay, right? And we simply modify this. First, we multiply G in the numerator and the denominator, and we have this form. And we take out zeta bar here in the numerator and take out this G bar in the denominator. Then you have this, and this was wrong. It's okay. Okay. So originally this is wrong. So the correct one is this. So if you multiply this to this, then you have this original form. Okay. So you have this equation. This is derived from the ET. Then with this, here if G is infinity, then HS becomes H infinity. Here if G is 0, this is 0, and this is 0, then this 0 becomes this one, right? Because this term is 0, this term is 0, then remaining is H infinity times this one is the HS evaluate with impedance element showed. Okay, so this is the alternative form, and this is the alternative EET, and this can be applied to here. Okay, we just reformulate the equation, and naturally this is the form you can use. This is the case for the load impedance. Okay, so because we are considering the ideal current sink, and this is the case of source impedance showed it. Okay, because we are assuming the ideal voltage source. Okay, so another one is this one. This one, I didn't, it's not a mistake, okay? But I would like to explain this again. So this is the loop gain analysis. TMS is the loop gain. So input is this one, and output is UI here, okay? And this is the EET equation with GS, okay? So GS is coming in. Initially it was assumed showed it, now it appears here. Then we need to evaluate this zeta bar is the condition this UI is 0. When UI is 0, this VO is 0, okay? So this is another short circuit condition. This is output null condition, because this condition can be established by selecting this pair UI prime. UI prime is one input, and IT prime is another input. UX prime is one input, and this is another input. So by selecting this wisely, the output can be 0. Okay, so that is the same as our previous simple example to make output 0 to output 0. Okay, so we have two input. This one will generate some positive voltage here, and the other one will generate negative voltage of that. Then they cancel. Okay, so this is a condition. So condition output is 0 is obtained by exciting this circuit with properly selected pair of UX. UX is this one. UX is this one, and IT. Okay, so we have one input here, another excitation here. With two excitations, you can always create this output null condition. Okay, you don't need to find out the null condition. Just assume this. Okay, so this is defined as output nullified. This is load impedance. No, this is the input impedance. Closed loop output nullified input impedance. Okay, we'll derive this once in the later. Okay, maybe the topic 16 we'll derive just once. Okay, so other than that, you don't have to derive this. Just understanding or using this relationship is enough. Okay. So, and this is the last, this one was the last lecture slide. Okay. So, summary of this thing, the transfer function of source coupled converter. Okay, this is the final result. So this one is easy. This one has two terms, and this has two terms here. Okay, and this term contains this. This is the input impedance of uncoupled converter, and this one is GIU is input impedance of uncoupled converter, and GI prime is open circuit. Open loop output showed input impedance of converter. So very easy to evaluate. And this is output is nullified. Okay, to nullify this one, the feedback should be connected. Okay, with that you are nullifying this. So this is a closed loop output nullified input impedance, and last one is open loop input impedance. Okay, so just to apply this. Okay, then you will obtain the transfer function gain of source coupled converter. Okay, so we covered the load coupled converter, and we covered here source coupled converter. So one of question might be what happens if source is connected, load is connected. Okay. So then we repeat, we apply this EET twice. Okay. Then you can obtain the transfer function, transfer gain of converter with their source subsystem and their load subsystem. Okay. That is coming later. Now we focus on this case. Okay. Source coupled converter case. Okay, this might be another typo. In filter coupled. Delete this. Input filter coupled. This is unnecessary. Input filter coupled boost converter, and this control is voltage mode control. Okay, so with this, we derive this. We'll derive this later. You don't have to derive this. I already derived that, and I made a table, and I'll show that table later. Okay, detailed derivation step was one paper, very tedious paper, just deriving this. Okay, I derived the 48 transfer functions there. Okay, 3 converters with 2 different control scheme and 4 transfer gains. So that is a very tedious job. Okay, and this is the simple in filter. But this can be anything. This is the simple example. I said this is a very practical problem, and many people suffered with this problem because if one have this converter, the guy should have this filter stage. Okay, then they interact here. So this might cause the instability because the input impedance seen through this behaves as minus resistance at low frequencies. If there is overlap between this GS and GIU, the system becomes unstable. To avoid that, they should analyze this. Okay, so it takes long time, maybe 20 years, something like that. Okay, so this is the filter stage. Then filter has its own transfer function, input-output transfer function. Without considering this, okay, that is a filter, input-output transfer function, AUF. AU stands for audio susceptibility, which is the same term as the input-output transfer function of filter. So this is simply the impedance division, G1 plus G2 in the denominator, G2 in the numerator, and the GS is, this is G1 and the G2, this is shorted, so this is a parallel combination of 2 impedances. Okay, so this is very trivial. Okay, what is not trivial is this one. I plot this GS and this is a GS, and I plot these 4 different input impedance. This is regular input impedance of uncoupled converter, and this is what? This is the output shorted open loop input impedance of converter, and this is the feedback signal nullified, output voltage nullified, closed loop input impedance of the converter, and this is the open loop impedance of the converter. Okay, so we need 4 different input impedance. They are absolutely necessary, and this is the plot based on this the analytical derivation. So I derived this. During that process, I used the EET many times. With that, I derived this, and later on, I have some curve will show up which compares this one. This is the simulation result with experimental measurement. They are almost the same. Okay, so GIU is this one. GIU is this one, and output nullified input impedance GI double prime is this one, and this is the GI triple prime. So this is the open loop output input impedance, and the GI prime is what? Open loop output shorted input impedance of the converter. So we have this 4 impedance curve, and we have 1 source impedance curve. Okay, so it looks complicated, And this curve is very sensitive to the topology of the converter. So boost converter, buck boost converter, and buck converter, they are different. Boost and buck boost converter are very similar, but no. Boost and buck boost are similar, but buck converter is quite different. Okay, and this also strongly depends on the control scheme. This is the case for the voltage mode control. If you apply the current mode control, the situation is entirely different. Okay, for some cases, for the buck converter with current mode control, this 4 input impedance becomes the same, almost the same. Okay, so there are many issues. So that is the reason why people got confused and they had a hard time to understand this problem. Okay, but we will go through one by one. So later on, we will derive this and just take this. Okay, so this is the definition of 4 different input impedance. This is the typical shape of this 4 input impedances. Okay, and very important factor is at low frequencies, GIU input impedance of uncoupled converter shows minus R characteristics at low frequencies, and this one GI double prime shows same characteristic, minus R characteristic for the wider frequency range up to this point. Okay, so maybe this source impedance looks like this. So for one example, suppose we have this situation, then converter is definitely unstable. Okay, because this overlap occurs at low frequencies. Okay, here overlap is here, so you cannot avoid some overlap. Okay, this is the open loop, so you cannot control the open loop impedances. That is open loop is open loop determined by power stage. Okay, so this is the analysis. Okay, it's the same plot. So GS, this is the GS source impedance, and 4 different input impedance of converter. This one is regular input impedance. This is output null, defined at output voltage null condition. Okay, and this is open loop, and this is the open loop with output shorted. So this one is open loop at high frequency. What you are seeing is just inductor at high frequencies. Okay, capacitor will be shorted, and the inductor becomes very large. Okay, that's right. Inductor becomes very large. So you have this kind of shape at high frequencies. Okay, and here is the situation. So this is audio susceptibility of from the input voltage through the input filter and through the converter. Okay, so we need this. This is the audio susceptibility of uncoupled converter should be multiplied with this. Okay, then this is what? This comes from EET. Okay, but you compare this. GS is this one. GS is this one, and the GIU is this one. So GIU is always larger than GS, so this term can be ignored. Okay, for the entire frequency, this will be smaller than 1. Then you forget about this. Then this the input-output transfer function of filter stage combined with the converter is this one, multiplication of this one. But in the log scale, this is the summation. Okay, so in here, this is AUU. Okay, let me put this one first. AUU. This is uncoupled input-output transfer function with this black curve. Okay, so you need to add this. You need to add AUF, but at low frequency, AUF is 0. Okay, because this is the low-pass filter, should be the low-pass filter. So at low frequencies, there is nothing to add. So they remain the same. And it follows this. Okay, this is the peak of this filter stage. And after that, at this frequency, the magnitude of this is 0. Okay, so this 0 means 0 is here, and you add negative of this, then the resulting magnitude curve is this one. Okay, there is some discrepancy. Okay, that may comes from the corner frequency or some error, and in this region, so this is this one. Input to output transfer function of uncoupled converter is this one, and the filter is low pass filter is providing this much of attenuation. Then you should add this one here. Okay, so this and this is the same thing. So by lowering this, it curve follows here, and this is the attenuation of filter at this frequency that should be added. This the attenuation of converter, so this one is the same as this one in the length. Okay, so you understand this. All right, this is a simple example, but not easy to understand. All right, and the output impedance. This is the expression. Okay, but we know this. This GIU is much larger than this for entire frequency. So this term is initially gone. Okay, because GIU is this one, and GIS is this one, same as the previous case, this case. So you forget about this for the entire frequency range. Then remaining is this one, okay? So when this GI prime is larger than this, you ignore this, and that becomes GOU, okay? So that frequency range is this range. So in this range, they same, okay? Source coupled and uncoupled generate the same output impedance characteristics, but in this there is overlap, okay? So this is the GI prime, this is the GI prime is here, okay? And this is the GS. So you have overlap of A and B should be added, okay? So this is the area of this A n plus B, okay? Because this one, GS, is larger than GI during this frequency range. So this will go up here, okay? So this is appearing here, and this region, the expression is this one, multiplication, but in low scale, there is addition. After that, the two curves, they merge together, because this can be ignored. Okay, so this is the case. Another one is this one, loop gain. Okay, so let's take a look at loop gain expression. We have this, right? But this is much larger than GS. That is true, always true. This is large, okay? And GS is coming here like this. Right? So you ignore this, and this is valid for the all frequencies, but for these frequencies and these frequencies, this can be ignored. But in the middle frequency range, this is larger than, which one is this? GI triple prime. This one is larger. GS is larger than this one. So you have B and C. They should be considered. Okay, but it comes in the denominator. So this is the uncoupled converters loop gain, and you have some dipping here. This much of dipping that comes from this area. Okay, right? So this explains everything about this. Okay, if there is no equation, something similar to this, you cannot understand this. It's very hard to understand. Sometimes it goes up, sometimes it goes down. Okay. That puzzle is solved with this EET equation. So EET equation is universally applied for any circuit analysis, and the best case is this case, where the source impedance and the load impedance, they are initially unknown, and later they are surely coming in to the converter. Then we evaluate this one, okay, and we understand this, and we predict some behavior, okay. Right? So everything is graphical. So we are assuming this data is available in Bode plot format using measurement or simulation or some other ways. Okay. Let's talk about the case of 2ET. Okay. Here extra element are 2. Okay. So this is the case G1, G2. Okay. We don't have any information about G1 and G2, but we are sure this will come later to form the system. Okay. For our case, this might be source impedance. This is the load impedance. Okay. So first adoption of the EET means we assume this is the shorted and this is the opened. Okay. This is the uncoupled converter model. And this is the shorted because we are thinking this is the source impedance. So we are using ideal voltage source. And this is the shorted. And this is the load impedance. Because we are using the ideal current sink that is open. So this is the beginning point. And introduce this one. You put GL here. Then you use the original EET equation. Okay. So this is the original EET equation. All right. So then you brought back to G2 or GL into the system, and you analyze this equation. Then you will have the transfer function of your interest analyzed. All right. So you brought back the load impedance GL, and next is you should bring in what? Source impedance. So this is the A. So I copy the A, same thing. So this is here. You are considering this load impedance is taken into account in this analysis, but still this is the shorted. Then we apply the second ET. Okay. So you brought back GS here. Then use this. This is what? The alternative ET. Okay. So this is the original ET, and on the result of this original ET, you added this term. This comes from the second ET. Okay. So you can repeat this again and again. Then you can extend this number of extra element 3, 4, 5 to infinity, something like that. Theoretically, okay. So ET is very general. Okay. So it can be applied to many practical situations. So this is one. This is they call it 2-element, 2EET theorem, and there is a paper talking about NET theorem. Okay, can be generalized to arbitrary number of this. Okay, the format is something different to this. Okay, but this one is much easier to our case because we attach the load impedance and we consider the source impedance. Then this one is better to use. Okay. The paper is very lengthy and very, very complicated, and their notation is so confusing, okay, because there are so many cases to be considered, but this one is very concise and precise, okay. This one is one example. So load coupled converter, so loop gain of uncoupled converter without this is this TMC, TMU. This is uncoupled converter, and we are considering this should be TML. Okay, so still this is the TML. TMC, I intended the TMC to be source coupled and load coupled all together. So this should be TML. Okay. This is okay, but I made a mistake here. Okay. So TML is related with TMU, and this is the modified EET expression. We went through this. Okay. So with this, the GOU divided by GL is only appearing. TMU appears two times, but this is better to analyze later. In the next topic, we will analyze this. Okay. So now this is the case of the TML. This is the This was a TML, load coupled converter. Okay. Then this GS is coming in. Okay. So this converter is load coupled and source coupled. So C means completely coupled. Both sides are coupled, completely coupled. Then you evaluate this and you add this additional term. This is the alternative EET expression. Okay, you understand this, right? Because this is a two-step procedure. I explained this here, that here. Same thing, right? Okay. All right. Okay. This is the end of lecture 3. Okay. So in the next lecture, we'll cover the lecture number 4. Okay, thank you.